Welcome to Buildora, where ideas turn into reality. From raw materials to real creations, we don't just imagine it, we build it. The goal of this project is to fundamentally transform a high-performance sport motorcycle into a machine capable of operating comfortably and safely in adverse weather conditions. At the center of this build is the Yamaha YZF 1000 R1, a motorcycle originally designed with one primary objective in mind: speed. Its aggressive riding position, minimal bodywork, and exposed cockpit prioritize aerodynamics and performance over comfort or environmental protection. The build begins with a full-scale structural mock-up. The first task is the construction of a wireframe skeleton that defines the outer shape of the cockpit. Metal rods are selected as the primary structural material due to their strength, flexibility, and ease of shaping. These rods are bent and positioned around the motorcycle to outline the roofline, sidewalls, and front windshield area. Chicken wire mesh is then attached between the metal rods. This mesh serves two purposes. First, it allows the builder to visualize the final shape of the cockpit in 3 dimensions. Second, it provides a base structure onto which shaping materials can be applied later. Together, the metal rods and mesh form a lightweight yet stable framework that establishes the overall geometry of the enclosure. At this stage, frequent adjustments are made. Clearance is checked around the handlebars, mirrors, and rider position to ensure that the cockpit will not interfere with steering or control inputs. Once the wireframe is complete, the next phase focuses on creating a solid, shapeable surface. Expanding foam is applied directly onto the chicken wire mesh using a spray applicator. As the foam expands, it fills gaps within the mesh and hardens into a rigid mass. This material is ideal for shaping complex forms. It is lightweight, easy to cut, and strong enough to serve as a temporary mold. After curing, the foam surface is rough and uneven. This is expected. Using hand tools and power sanders, excess material is gradually removed. Once the desired shape is achieved, a layer of filler is applied to smooth out surface imperfections. This step is critical, as the quality of the mold directly affects the final transparency and appearance of the cockpit canopy. Any uneven areas, sharp edges, or inconsistencies could result in distortion once the transparent material is formed. With the mold complete, attention shifts to one of the most technically demanding components of the project: forming the transparent roof. To shape the canopy, a custom heating device is constructed. This device is designed to evenly heat large sheets of polycarbonate, allowing them to soften and conform to the complex curves of the mold. The frame of the heating unit is built using square tubular steel bars welded into a rectangular structure. Strength and stability are essential, as the frame must withstand sustained high temperatures without warping. A large polycarbonate sheet is selected for the canopy. Polycarbonate must reach a temperature between approximately 150 and 160 degrees Celsius to become flexible without losing structural integrity. As the material softens, gravity causes it to sag slightly, indicating that it is ready for forming. At the correct moment, the heated sheet is transferred onto the mold. A vacuum system is activated, pulling the polycarbonate tightly against the mold surface. This process, known as vacuum forming, once fully formed, the canopy is left to cool naturally. After cooling, excess material is trimmed away and the edges are sanded smooth to create a clean, professional finish. The process is repeated to form additional sections of the cockpit walls. Each piece must align perfectly with the others to maintain structural integrity and visual consistency. Once confirmed, holes are drilled through the polycarbonate and metal frame. Rivets are installed to permanently secure the canopy, chosen for their strength and ability to distribute load evenly. In areas requiring flexibility, bolts and washers are used instead. Additional aluminum support brackets are fabricated and installed along the edges. These reinforcements help the cockpit withstand wind pressure and vibrations during operation. Visibility presents another challenge. The original rearview mirrors now fall within the cockpit's boundaries. To resolve this, new mounting points are created, and the mirror stems are shortened to extend beyond the enclosure without creating excessive drag. Safety checks are performed to ensure that all fasteners are secure and that the cockpit remains rigid under movement. With the build complete, the transformation becomes clear. The motorcycle is no longer exposed to the elements. The enclosed cockpit reduces wind resistance, shields the rider from rain, and improves visibility during poor weather. The windshield prevents water droplets from obstructing the rider's view, and the curved surfaces maintain aerodynamic efficiency. This project demonstrates how careful engineering and material selection can redefine the purpose of a vehicle. What began as a race-focused machine has evolved into a practical, all-weather motorcycle without sacrificing balance or control. If you enjoyed this video, subscribe to Buildora and watch more amazing projects like this in future.